Electrostatics, Regents review 4. All right, let's knock this one out quick. When 2 point charges distance d apart, the magnitude of electrostatic force between them is F. Distance between the point charges equals to 3. Electrostatic force between each will be. All right, so if you triple the distance, right, R is that, R, 3R, it's the electrostatic force KQ1, Q2 over R squared. Force is directly proportional to 1 over R squared. So if you're tripling it, it's like going from this to 1 over 3R squared. So it ends up being 1 over 9. Really common thing. Moves farther apart, it gets weaker, so it's got to be 1 or 2. Then I just look and say, okay, is the thing I'm changing squared or not? Since it's squared, the effect is squared, so it's 1/9. You don't really need to do all this. You can literally just think about it like that. It's getting weaker because they're getting farther apart. And since the variable is squared, the effect is squared. All right, how much work is required to move an electron through a potential difference of 3 volts? Work is QV. On your reference table, it's V equals work over charge, so we rearrange it to be that very often. This is with that other problem. So we go work equals Q, and electron's charge is on the front of the reference table. Right there, 1 elementary charge is 1.6 times 10 to the minus 19th coulombs. It's up to you to know that an electron is negative 1 E. You don't need the sign on this. All right, so it ends up being 2. Base your answers 30, 31. And this below. Okay, so 2 meters apart, negative 1.6 times 10 to the negative 6, positive 1 times 10 to the negative 6. What's the magnitude of the electric force? F equals K, Q1, Q2 over R squared. So F equals K, which is 8.99 times 10 to the 9th. I always just use 9. So 9 times 10 to the 9th. Newtons times meters squared per coulomb squared. I'm just going to put the units in here like I would if it was a short answer question. I'm running out of space here. It's 1.0, negative 1.6. You don't really need the signs on these. Divided by 2 squared. We're just plugging and chugging here. All right, so 9 double E 9 times 1.6 double E negative 6 times 1.0 double E negative 6. All right, divided by 4. 0.0036 newtons, which would be that one. Right, 0.0036 newtons is 1, 2, 3, so there we go. Very good. Two sphere, if these now are touched together and separated, what will the charge on sphere A be? Okay, so you got to find the Q total here. So it's negative 1.6 and positive 1. Just add those two numbers together. So the total charge is negative 6 times 10 to the negative 0.6 times 10 to the negative 6 coulombs, which is negative 6.0 times 10 to the negative 7th coulombs. That's the total. So when you separate them, they each take half, right? So it's going to be negative 3 and negative 3 times 10 to the negative 7th. Okay, so they split the charge when you touch them together. Number 7, electric force of 8 newtons exists between 2 point charges Q1 and Q2. If the distance between is doubled, okay, the new electrical force will be, okay, so it's F is proportional to 1 over R squared. This must have been from another Regents. It's basically the same question as that first one we did. So you're doubling, so that means the new force is going to be 4 times the original force. Oh no, 1/4, right? Because it's going down. So it's going to be 2 times 10 to the -5th. They're getting farther apart. Distance is doubled, so going from that to that, R to 2R, the force is 1/4. It's weaker. Beam of electron passes through an electric field where the magnitude of electric field strength is 3 times 10 to the 3rd newtons per coulomb. What is the magnitude of electric force exerted by the electric field in each electron? F equals QE. The reference table gives it to you as E equals F over Q, which we rearrange into that. The charge of the electron is 1.6 times 10 to the -19th coulombs. The electric field strength is 3.0 times 10 to the 3rd newtons per coulomb. The coulombs are going to cancel. So 1.6 times 10 to the -19th times 3 times 10 to the 3rd is 4.8 times 10 to the -16th newtons, which looks like 2. All right. Very good, very good. How much work is required to move 3 coulombs of electric charge a distance of 0.1 meter through a potential difference of 9 volts? All right, work equals QV. Again, reference table gives it to us as V equals work over charge. Again, this is probably from a different Regents. Here we go. So Q is 3 coulombs. The volts is 9 volts, so that's 27 coulombs times volt, which is 27 joules. Remember, coulombs times volts. Volt is a joule per coulomb, right? So the coulombs cancel, bringing a joule. Very good. This one here, which one is correct? Or no, sorry. What is the sign on charges A and B? Well, since the arrows are pointing in on both of them, you know they both must be negative. And we know that shape is when they're similarly charged, right? The field lines diverge from each other. All right, I love this one. A is has excess electrons, so A is negative. B is neutral, right? So you got to have the same number of electrons and positive charges on it. 1 and 3 here are not neutral. These two are, and they're both polarized. So it just depends on which way is it going to polarize, right? So the electrons can move. They're going to move over here. Some of the electrons are going to move over there, right? And it's going to leave this side positive. So it'll be 4. Very good. I love that question. Good one. All right. I like this couple pages. A lot of conceptual, not too many calculations. I like the conceptual questions myself. 2 points A and B are located within the electric field produced by a -3 nanocoulomb charge. Point A is 0.1 meter to the left of the charge. Point B is 0.2 meters to the right of the charge, as shown in the diagram below. Compared to the magnitude of the electric field strength at point A, the magnitude of the electric field strength at point B is... All right, so field strength is force per charge, okay? The force is K Q1 Q2 over R squared. So the electric field strength here depends on, we could measure by the amount of force it applies to a charge. The electric field exists, right? Like if I drew the electric field of this, right? It's going inwards because field lines show us the direction that a positive charge would travel in, right? So the field exists. There's no force until an object is put there. So you got to think about, for this one, the fact that if I do put a charge here, it'll experience a force, and the one that's closer will be stronger. So this is asking us to compare B to A. So A has to be weaker, so it can't be those two. Or sorry, B has to be weaker than A. All right, so it has to be one of these. And my gut says it's this one. 1/4 is great because of the r squared dependency. Since the field strength would be proportional to the force, and the force is proportional to 1 over r squared, this one's twice as far away, so it would have 4 times less force. Which combination of units can be used to express electrical energy? So I guess you got to realize electrical energy would be the work that could be done. So work equals QV, coulombs times volts will give us energy. And again, that's equivalent to, let's see, is capital as well. That is equivalent to joules, anyway. All right, cool. 2 identically sized metal spheres on an insulating stands are positioned as shown below. The charge in sphere A is -4 times 10 to the -6 coulombs, and the charge in sphere B is -8 times 10 to the -6 coulombs. 2 spheres are touched together and then separated. The total number of excess electrons in sphere A after the separation is, all right, so if they touch together, they're going to split whatever the total charge is here. So Q net, or Q total, whatever you're going to say, is -12 times 10 to the -6 coulombs. So then they're going to share that. They're each going to take -6 times 10 to the -6 coulombs. And that's our answer. But, oh, wait a minute. This is asking for the number of excess electrons. So we got to take that. We got to say, okay, 6 times 10 to the -6 coulombs is equivalent to 1 per 1.6 times 10 to the -19th coulombs. We got to be able to convert this. There's actually this here. 1 elementary charge is 1.6 times 10 to the -19th, or 1 coulomb is 6.25 times 10 to the 18th elementary charges. So I could have multiplied that by this number, but I always think of it like this. So there's different ways to do it. 6e -6 divided by 1.6e -19. Oops, my calculator was not on. 6e -6 divided by 1.6e -19 gives us 3.8 times 10 to the 13th fundamental charge particles. Okay, very good. All right, last page. I like this page a lot. I like this last question. It's a good multiple choice question. Which diagram represents the electric field between 2 oppositely charged conducting spheres? All right, so first thing to check are the shapes, right? Like, I've seen all these shapes before. There's no crossing lines, so the shapes look okay. But now we got to look at the arrow directions. All right, out of positive, good. Out of negative, nope. Into positive, nope. Out of positive, into negative, okay, that looks actually correct. Into positive, nope, can't be that, it's 3. All right. 2 conducting parallel plates, 5 times 10 to the -3 meters apart, are charged with 12-volt potential difference. Okay, so we got quite a bit of information here so far. And the force on the electron is that many newtons. All right, on the diagram answer, draw 3 field lines, at least 3. I'm going to draw 4 just because that's what I did in one of my classes, and that feels better than just 3. For some reason I avoid wanting to make one through that electron. I don't know if that's pretty. You need at least 3, so 4 is good. The big thing there is to make sure that the lines are touching and the arrows are pointing away from positive. Okay, force on the electron will be up because it's going to be drawn up. It's going to be attracted to the top plate and repelled from the bottom. So there's a force of attraction to the top. And there's also a force of repulsion from bottom. All right, so it's gonna go up or towards the positive plate. Okay, I'm gonna have a student coming in here shortly, but I should be able to get through this. Calculate the magnitude of electric field strength between the plates in newtons per coulomb. All right, E equals F over Q. All right, so the force is 3.8 times 10 to the negative 16th newtons. Answer the question you've been given, right? Don't try to use stuff prematurely. Identify the variable, the equation. Since it's a 2-point question, it's got to be one equation from the reference table. It can be done other ways, possibly, but if it's 2 points, you can definitely do it with one question from the reference table. And then the charge of it, since it's an electron, 1.6 times 10 to the minus 19th coulombs. So let's do that math. 3.8 times 10 to the negative 16th divided by 1.6 times 10 to the negative 19th is 2400, 2375, but 2 sig figs, 2400 newtons per coulomb. And if you forget what a unit is, find it earlier in the test, right? We probably had an electric field strength somewhere in the test. Let's go find the right unit. Or just write down what you get when you do the algebra. Describe what happens to the magnitude of the net electrostatic force on the electron. Well, the force is QE. The charge doesn't change. So since it remains constant, remains the same. That's all you really have to say, but I'm going to elaborate for video's sake. Since the field is uniform, that means the field lines are all parallel to each other. The force is constant. Now, but you might say it's getting closer to the top plate, so it's got to get stronger. Yes, the attraction to the top plate gets stronger, but the amount that got stronger by is equivalent to the amount the repulsion from the bottom plate got weaker. So it ends up being a wash, essentially. All right, so there you go.